Okay, got a warm-up question here for you to think about. Give you a minute or two to do that. Give everybody a second to filter in. Okay, so we're starting off thinking about the word multiplication, which I think I spelled right, although there's a lot of letters there. We want to know how many ways are there to rearrange these letters. That's question one. And then question two is, what if we want to rearrange the letters, but we don't want to have two I's next to each other? Then how can we do it? So I'm interested in thoughts for either question. Or any thoughts at all? Happy Thursday morning. Everybody's still waking up. Okay. So, first things first. How many letters in multiplication? Let's get that down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like 14 letters. So we have 14 letters. If we just did 14 factorial, 14 factorial gets us all of our different arrangements. But we do have to be careful because some of our letters are repeated. So we've got I. We also have repeated T's. And repeated L's. I think everything else is unique. MUPCAON, yeah. Good. So if we just did our factorial, our 14 factorial for the 14 letters, we have to be careful because whichever order our L's in doesn't really matter. Whichever order our T's in doesn't really matter. So what are our repeated letters? We've got a pair of L's, a pair of T's, and a triple of I's. So we want 14 factorial over 2 factorial, 2 factorial, 3 factorial. Which is good. Feels like we've converged on that in the chat. So good. Okay. And this is very similar to a problem we did last Thursday, I don't remember at this point, about banana. How many ways can we rearrange banana? Same type of idea here. But now I want to ask an additional question. What if I'm not allowed to have two I's next to each other? Yeah, so one option we have, it's a good suggestion from chat, we could take this number and we could subtract off the number of ways of making sure two I's were next to each other. But because we have three I's, that gets a little bit complicated. Right? We can combine two of the I's together to make sure that they're next to each other, but then there's still that other I, and it's a little bit more complicated than necessary. So I want to use this problem, which is similar to something we've seen but has a unique twist, and use it to investigate what's going on. So first, there's a really good idea that chat's come up with, I think, at the core of both of the ideas in the chat, which is, can we combine the I's together and make a group? So if we had a simpler word, something like icicle, here I've got 6 letters, so I've got 6 factorial ways to arrange them, but I've got a repeated I and a repeated C. So I've got 6 factorial over 2 factorial times 2 factorial ways of doing this. And if I want to make sure that no 2 I's are consecutive, I can say, well, what if I did 5 factorial over 2 factorial, and I treated the 2 I's as a single unit? I linked them together. This says my letters are only I, C, C, L, and E. And then I can unbox my I's and turn it back into an arrangement with 2 I's next to each other. And now if I want to have icicle without 2 I's next to each other, I can subtract off this number that I've calculated. Totally works. But now when I have a third I, things start to get a little bit more complicated. Because now I have one of these I's that's linked together and a third I that isn't. So I really am sort of treating the I's separately. Oh, can I explain what's going on here? Sure. So I want a rearrangement of icicle where I do have 2 I's together. The idea is if I want to avoid the double I take the total number and I subtract off the number that do have the double I. And in order to force the double I to happen, I'm going to collect my letters, except I'm only going to use 1 I when I do my arrangement. And then after I've done my arrangement, after I come up with an order, maybe it's ICCLE, or maybe it's ELCIC. After I do my arrangement, I'm going to turn my 1 I into 2 I's next to each other. And that's how I'm going to guarantee that I have 2 I's right next to each other. And I think this works really good, really well, if... explain the 2 factorial. This is for the 2 C's. I'm arranging 5 letters. So 5 factorial. But I have 2 C's and I don't care about the order. So 1 I, 1 L, 1 E, and 2 C's. So I'm dividing by 2 factorial there. I think this works well because we have 2 I's. Once I add in a third I, things get more complicated. So I want to talk about just another trick that we can use. And that's going to be to do a 2-step process. Step 1 is going to be to arrange everything except for the I's. And then in step 2, we'll place the I's so that they're not next to each other. So how many ways do I have of rearranging the letters of multiplication except for the I's, not including the I's? In other words, how many ways do I have of doing step 1? Yeah, really good. 11 factorial divided by 2 factorial, 2 factorial. Right, very similar problem to part A. But I don't have to worry about the i's. And I now only have 11 letters. So 11 factorial over 2 factorial, 2 factorial. Now, I have 11 letters set out in a row, right? Just as an example, maybe I have A, C, L, L, M, N, O, P, T, T, U. Maybe that's the particular arrangement that I settled on. Now I want to do step 2. I want to place my i's down. How many places do I have to put an I? 11 letters here. How many different places in this list of letters is there to plop down an I? Yeah, really good. We've got 12 different options. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each of those 12 spots can hold 0 or 1 i's. Can't hold 2 because I'm not allowed to have 2 i's next to each other. But any one of those 12 slots, I can put an I there. So how many ways are there to plop down my 3 i's so that I don't have 2 next to each other? How do I pick the 3 slots? 2 to the 12 is a good idea. 2 to the 12 is saying for each slot, I decide, is there an I there or not? But that's not quite right because I only have to place down 3 i's. Right? So I can't have yes, 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 because that would be 4 different i's that I'm putting down. And then 12 times 11 times 10 is another good guess, right? I've got 12 options for the first I, 11 options for the second I, 10 options for the third I, except that all the i's are the same. So the order that I place down the i's doesn't matter. So 12 choose 3 is exactly the one that we want. Which, by the way, is why this warm-up question comes right after we learned about choosing. I have these 12 spots. It doesn't matter what order I choose them in. I just need to choose 3 of these 12 slots for my I. So maybe this particular one, I put an I here, here, and here. And now I have an arrangement of the letters of multiplication where the i's did not end up next to each other. Right, and then to answer part B, I have a 2-step process for generating one. Now I use rule of product, and so my final answer is 11 factorial over 2 factorial, 2 factorial times 12 choose 3. It's a tricky question. It's probably not the unique way of solving this. There's probably a way of making this idea work. But I like this problem as just as another tool to add to your toolbox. And another idea. Something else to try. Okay. So let's keep going. Last time we were talking about the difference between an algebraic proof and a combinatorial proof. I want to keep going with that idea. Look at another theorem. Okay, really good question before I move on. Why did we subtract here but multiply here? So we've got two different techniques going on. This is a technique we talked about last time, where in order to count the number of times where something does not happen, we count the number of times where it does happen and subtract that off from the total number. We decided that using that technique for this part B was just going to be hard. It was going to be hard to figure out how to make two i's show up next to each other and then subtract that off. Because we had three i's to deal with, but only two had to be next to each other, there was just something more complicated going on. And so calculating the correct number to subtract was not going to work out nicely. So instead, we came up with an alternate approach. Now, it's worth noting, this alternate approach also works in this problem. I could also say that this number is 4 factorial divided by 2 factorial. That's rearranging my C, C, L, and E. And then I want to multiply by how many places I have. So if I have C, C, L, E, now I have 5 places to plop down an I. And I want to choose 2 of them. Times 5, choose 2. And these two expressions should give me the same answer. So this is 6 times 5 times 4 times 3 over 2 is 6 times 5 times 3 times 2 is 6 times 6. 6 times 6 times 5. So that's 30 times 6 is 180. Minus 5 factorial over 2 is 5 times 4 times 3 is 60. So this gives me an answer of 120. This is 4 times 3 is 12. And 5 choose 2 is 5 factorial over 3 factorial, 2 factorial. So that's 5 times 4 is 20. This is also giving me 120. Right? Two different ways getting the same answer, which I've confirmed now numerically. So maybe there is a way to do the multiplication question with subtraction instead of with multiplication. But this is the method I wanted to talk about. Okay, so hopefully that answers that. So let's move on now. Theorem. 2 to the n is equal to the sum from I equals 0 to n of n choose I. And this is for all n positive integer. Really, I guess, I mean non-negative integer, but I'll stick with positive integer for now. Okay. And I want to talk about doing a combinatorial proof. So I'm not going to prove this algebraically. If I was going to prove this algebraically, I would probably do it with induction. And I would prove it for a base case, like n equals 1, and then I'd have to figure out some way of doing the algebra and the expansion. I'd have a 2 to the n plus an n plus 1, choose n, something like that. It would get a little messy. Because it'd actually be really messy because these binomial coefficients would all have n plus 1 instead of n, and we'd have to do a lot to make this work. So instead, I want to talk about a combinatorial proof. And my proof should be familiar because we've actually already talked about this inequality. Before I give it away, when did we see this? When did 2 to the n come up? It was a week ago already, way back on Thursday. What did 2 to the n count for us? Yeah, true or false, yes or no, pizza toppings. So remember, way back on Thursday, a whole week ago, we were trying to figure out how many different pizzas there were. There were 37 toppings, and we decided the clever way of thinking about it was to go through each topping and decide yes or no. That counts the total number of pizzas, so somehow this should also be counting the total number of pizzas. And we had this other idea for counting the number of pizzas, and it didn't work out at the time. It was to break it down into how many toppings we had. This is doing exactly that. It's breaking into cases based on how many toppings do we want on our pizza. If we want I toppings, there are n choose I ways to make a pizza with that many toppings. Now we just have to write that down in a proof. So we count the number of ways to make a pizza with n possible toppings. In 2 ways. Method 1. For each possible topping, we decide if it's on the pizza or not. So we define a sequence of decisions. Where for each topping, we decide whether to put it on the pizza or not. By the rule of product, there are n steps, each with 2 options. So 2 to the n pizzas. Okay. And method 2, we first break into cases based on how many toppings end up on our pizza. How many toppings end up on the pizza? And then how many ways are there to make a pizza if you know that there are exactly I toppings? There are n choose I ways to make an I topping pizza. I'm going to go on to the next page. By the rule of sum, there are sum from I equals 0 up to n. Those are all my different cases for number of toppings. I could have 0 toppings all the way up to n toppings. And choose I, different pizzas. Then just one nice conclusion, because these quantities both count the number of pizzas two to the n is equal to this sum I equals 0 to n, and choose I for any n natural numbers. Okay, and this is a completely rigorous proof of this theorem. Did I write it talking about pizzas? Yes, I did. If you look up this proof in a fancy math textbook, it's not going to talk about pizza toppings. It's going to talk about subsets of a set with n elements, because mathematicians are boring. But there's absolutely nothing wrong with talking about pizza toppings. This proves that these two quantities are equal, because I've shown that both sides of this equation count the same object. That object could be subsets of a set with n elements, or it could be pizzas with n possible toppings. Both ways get us there. Okay. Yes, absolutely. If you have a test or a quiz and you decide that a combinatorial proof is appropriate, I will caution you that if your example starts getting very silly, it's possible that you'll lose the grader. They just won't be able to follow your argument. But this, I think, is a very natural example. I think it is very clear, at least to a Western audience who's used to pizza and different toppings and putting toppings on their pizza, perfectly fine way to talk about this. If you prefer, feel free to write this with sets. We count the number of ways to make a subset of a set with n elements in 2 ways. We define a sequence of decisions for each element. We decide whether to include it in the subset or not. By rule of product, there are n steps, each with 2 options, so 2 to the n subsets. Method 2, first we break into cases depending on how many elements end up in the set. There are n choose I ways to make a set with I elements, a subset with I elements. By the rule of sum, there are this many subsets. Because both quantities count the number of subsets, these things are equal. Proof doesn't change drastically. Now, if you're using some very strange or some very niche example, I don't know. I can't think of an example that's hard to think of, but you get the idea. I once had a student write something, this was like an early 2010s meme, and there was like a rule of product question, and the steps that they chose were like getting on the floor and walking the dinosaur, which was an ancient meme, and the grader was just like, what are you talking? I have no idea what this is. So, you know, you should feel free to be creative to a point, and then don't push it too far. But a fair question. Okay, let's keep going. I think that was enough stalling that if anybody had questions, they would have asked. So this result, this equality, actually comes from something else I want to talk about. I want to look at what happens when we try to expand something that looks like x plus y to the n power. So we know what this is. This is going to look like x plus y times x plus y times a whole bunch of times x plus y, total of n of these multiplied together. And since we've all gone through high school, we know that this is not equal to x to the n plus y to the n, at least as long as n is bigger than 1. Right? We've got to multiply all of these out, distribute all of these through. So here's my question. What is the coefficient of the x to the n term? I can think about multiplying these all together. I'm going to get some terms with some x's, some terms with some y's. But what coefficient is going to be in front of x to the n? How many different ways are there? Yeah, there's only one way to get x to the n. Just one. Because if I want x to the n, in every one of these things I'm multiplying together, I have to pick the x. So x times x times x times x. There's only one way of doing it. If I ever pick a y instead, then not only will I not have the correct power of x, I'll also have some y's in there. But my next question is, what is the coefficient of x to the n minus 1 times y? This is another thing that can pop up, right? I can have n minus 1 x's and then a single copy of y. And to figure this one out, I want you to think about how one of these terms comes out of this multiplication. I'm always going to get n total things when I multiply this all out. So if I want a particular term, what I'm really doing is I'm going x plus y by x plus y, one at a time, multiplicand by multiplicand. And I'm picking x or y from each one. So if I want to get an x to the n minus 1 times y, I could pick x, 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 finish on y. Or I could pick x, 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 y, last x. Or x, y, x, 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 x. Or I could pick y first, and then x, 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 x. How many different ways are there to choose my y out of these? N. I've got n different places where my y could come from. So if I did start multiplying this out, I would get x to the n plus n times x to the n minus 1 times y. And then let's keep going. What is the coefficient of the x to the n minus 2y squared term? How many ways can I end up with 2 y's? Everything else is an x. Yeah, I've got these n terms. I have to pick 2 of them to be y. Everything else I'll choose x. But from these n things, I pick 2 of them where I choose the y. In every other instance, I choose the x. So this will be n choose 2. And I'll get n choose 2 x to the n minus 2, y to the 2. And I can keep going. And what this gives me is the binomial theorem. Keep this up for another second. Theorem. This is the binomial theorem. The binomial theorem says that x plus y to the n power is equal to this sum. I starts at 0 and runs up to n. Of n choose I, x to the I, y to the n minus I. Okay, let me do an example real quick. A couple examples. X plus y squared. This is x plus y times x plus y. All right, we can FOIL first, outer, inner, gives me yx, but I'm going to write that as xy. And then last gives me x squared plus 2xy plus y squared. And this is also 1 times x squared times y to the 0, because anything to the 0 is 1, plus 2 times x to the 1 times y to the 1, plus 1 times x to the 0 times y squared. And 2 choose 0. Remember, 2 choose 0 means 2 factorial over 0 factorial, 2 minus 0 factorial. 0 factorial is 1, so I get 2 factorial over 2 factorial, 1 over 1 times 1. I'm just getting a 1 there. Times x squared times y to the 0, plus 2 choose 1, x to the 1, y to the 1, plus 2 choose 2, x to the 0, y to the 2. I match this. I think I may have my coefficients backwards, but you get the idea. And just for completeness, let's do it with x cubed as well. X cubed, you might have this one memorized. Is x cubed plus 3x squared y plus 3xy squared plus y cubed. This is exactly our 3 choose 0, x to the 3, y to the 0, plus 3 choose 1, x to the 2, y to the 1, plus 3 choose 2, xy squared, plus 3 choose 3, x to the 0, y 3. Y is the coefficient depending on the number of ways we choose y. Really good question. Remember this inequality we saw earlier. N choose k is equal to n choose n minus k. So if you prefer, we're either picking how many times we choose y or picking how many times we choose x. You can think of it in either case. The other way of thinking about the coefficient of the x to the n term is not I never choose y, it's I always choose x. Instead of saying there's n ways to choose y once, there's also n ways to choose x n minus 1 times. That's a good question. Let me just pause. Other questions? About the binomial theorem. Okay, let's do an example. this related to Pascal's triangle? Yes. You're about 5 or 6 minutes ahead of me. Let's do an example with the binomial theorem, and then we'll take our quick break, and then we'll come back and we'll talk about Pascal's triangle, because Larry is too quick for me. I do want to talk about that. It's even in my notes. So, example, what is the coefficient of a cubed b cubed in 4a minus b to the 6th power? Give everybody a second to think about that. Maybe I should sneak the binomial theorem back up here so we have that available to us. So what's my x in this case? This is good. My x is not a. My x is 4a. Right? Everything in this first spot is my x. What's my b what is my y in this case? Negative b. Really good. Right? This is a plus sign. How do I write this in a way that makes this match up? I need to write this as 4a plus negative b, all to the 6th power. And now this gets to be my x, and this gets to be my y. And now I can use the binomial theorem. What's my I? What term do I care about? I think Daniel had it earlier. The term I'm interested in is when I equals 3. Good. Which means the binomial theorem says, right, when I is 3, I'm going to get this to the 3, and then n in this case is 6, so 6 minus 3 is also 3. So what I'm going to get out of this is 6 choose 3. My x is 4a cubed. And my y is negative b cubed. And so if I want the coefficient, I just have to do a little bit of work here. Negative b cubed is a minus sign out front. Negative 6 choose 3 times 4 cubed. I don't know what 4 cubed is. I could work it out. I'm sure it's 2 to the 6th, so 64. Whatever. 4 cubed. A cubed, b cubed. So my coefficient is negative 6 choose 3 times 4 cubed. Using the binomial theorem. So, right, we wanted to squeeze it into this form So I had to squeeze my 4a together to fit inside my x variable. And to change the minus into a plus, I had to do a plus negative b to squeeze my negative b into the y variable. And then I can plug those in, and I can focus on the a cubed, b cubed part by pulling all of the coefficients out front. Okay, let's take our break. 2 minutes. Get up and stretch. Go grab some water. Run to the restroom, whatever you need. We'll come back at 9:19 Winnipeg time. I'll be right back. I need my water. I guess for everybody watching this on YouTube later, probably just skip through these parts, but I think the breaks are helpful for actual live lectures where you can't really pause and go back and read things again. But now I've ruined your fast forwarding on YouTube later because you've stopped to see what I'm trying to say now. But I'm not really talking about the lesson. Sorry. Wow, okay, so Ashley's here for the live lecture and is then going to go back and watch it again later. That's dedication. I'm impressed. Takes a longer break. That's fair too. I do. YouTube tracks how many views you get, obviously. And I do get I get more views on the YouTube video than there are students in my section. So either students from other sections are watching, or people are watching multiple times, or I don't know what's going on, but do I think university lectures will be recorded going forward? Even before everybody was sort of forced online for COVID stuff, there was a big push to record lectures. Like MIT has full courses all recorded. But the technology to record in-person classes are just really, really different than something like this where it's delivered remotely. So I'm not sure. I think if it's a priority of the university, it can be done. But it's also a non-zero cost to the live component. Yeah, I don't know. Anyway, I've got 9:20 even. Snuck an extra minute of break out of me. So let's get back into things. And let's go back to Larry's question about, does this have anything to do with Pascal's triangle? It does, in fact. So you might have known or learned at some point that if you want to find the coefficients of x squared or x cubed, there's this funky little thing that can help you. This triangle of values. And to create this, I always start with a 1, and then I add together the two values above me. So 3 and 3 is 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. And so this is called Pascal's triangle. And beside just being like a fancy thing to draw, it has lots of patterns in it. You can see this diagonal is all 1s, this diagonal is 1, 2, 3, 4, 5. This diagonal 1, 3, 6, 10, 15. These are triangular numbers. You've got some symmetry going on, but also x plus y to the 6th power is x to the 6th plus 6 x to the 5th y plus 15 x to the 4th y squared plus 20 x cubed y cubed plus blah, blah, blah. 15, 6, 1. You can use the triangle to tell you these coefficients. Which must mean that these coefficients are related to this binomial theorem, to this n choose I, which is why we call this a binomial coefficient. N choose k is a binomial coefficient because it comes from this binomial theorem. And actually, that means Pascal's triangle is trying to tell us something. Pascal's triangle suggests the following equality. How do you get something in Pascal's triangle? You add this together, and you get the thing below it. So that tells me if I pick a particular value in here, and I say, so this is, let's rewrite Pascal's triangle in terms of our coefficients, our binomial coefficients. This is 0, choose 0, 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. I'm going to stop there just because it's a lot of writing. This suggests if I pick two coefficients, something like n choose r minus 1 plus n choose r, if I add these two together, I should go down a row, so my n is going to increase, and I get that choose r again. This is an identity that's suggested from Pascal's triangle. This isn't a proof that this is true. It's just, well, if that's how Pascal's triangle works, then that's how binomial coefficients work. This should be true. So let's prove this. Look at another example of a combinatorial proof. You can do this algebraically. This one's not terrible to do algebraically, but there's a lot of factoring going on. So instead, let's prove this with another combinatorial proof. Theorem for all n and r in, this time I'll be more precise, the non-negative integers with 0 less than or equal to r less than or equal to n choose r minus 1. Sorry, that looks kind of like an n. N choose r minus 1 plus n choose r is equal to n plus 1 choose r. And again, we'll do a combinatorial proof. We'll count the same thing in both ways. One of these sides is way simpler. One of these sides is n plus 1 choose r. So I'm going to count something in two ways. The thing I'm going to count is choosing r objects out of n plus 1. I could talk about choosing r toppings out of n plus 1 options, but I'll be a little bit more mathematic-y this time, and I'll say we count the number of subsets of size R from a set with n plus 1 elements in two ways. So method 1, just pick your R elements. This can be done in n plus 1 choose R ways. So this one, nothing fancy going on. We're just picking our elements. For method 2, I want to talk through it with you. What does the plus sign mean? What am I going to end up using in this method because there's a plus sign? Good. Plus sign means rule of sum. I'm adding something together, which means there have to be two separate cases. Yeah, really good. So that should get you thinking, what are those cases? And the other thing to think about is that here I have n plus 1 options, but here I only have n options. So I have two cases, and I have one fewer option. What did I do? The thing I did was I either included that element or I didn't. So consider two cases. The n plus 1th or n plus 1st, depending on your preference, object or element, I'll say, is included in the set or it is not. I guess I actually want R to be greater than or equal to 1, by the way. I'm just realizing, because I want R minus 1 to be greater than or equal to 0. So this should be R greater than or equal to 1. I'm just going to make that change. Yes, so I've already decided, inside of each case, I've already decided if this n plus 1th element is going to be included or not. If it is included, we need R minus 1 more things for our set. Additional elements. And there are n elements left to choose from. So n choose R minus 1 possible sets. On the other hand, I can decide not to include the n plus 1th element. On the other hand, if n plus 1th element not included, then I still need R total elements, but I only have n left to choose from. From n remaining. So n choose r possible sets. And now we do the thing that we said we would have to do by the rule of sum. These are our two separate cases. There are n choose r minus 1 plus n choose r possible sets. And then let's write a nice concluding paragraph. So because both methods count the R subsets of n plus 1 elements, n choose r minus 1 plus n choose r is equal to n plus 1 choose r. And this is called, because it comes from the triangle, this is called Pascal's identity. So you may see it referred to like that. Okay, slightly wordy proof, not too bad. Confused at method 2. Okay, let's talk more about method 2. I even have this nice space over here that I can use for an example. So I'm looking at my universe of elements, my set of elements, and I have n plus 1 of them. And of these, I want to pick r of them to be my subset. We could even make it easier. We could make this the numbers 1 through n plus 1. So method 1, just for completeness, I've got n plus 1 things. I choose r of them. That's my set. For method 2, I'm considering two different cases. There's a case where my set does contain n plus 1, and there's a set where it doesn't. So, for example, if n was 3 and r was 2, some of my sets will contain 4, right? I might have 4, 1, 4, 2, and 4, 3. But other ones of my sets won't. 3, 2, 3, 1, 2, 1. Those are my options. So I'm breaking into cases. One of my cases is when I have my biggest number, n plus 1. And the other case is when I don't have my number, my biggest number. If I do have my biggest number, then I've already picked one of my elements. So now from 1, 2, and 3, I only need to choose one element because I already have the other one. In the sets where I don't include 4, I need to choose 2 elements, still from 1 to 3. And then I add these two cases together. And that's giving me my total number. Okay, one more quick thing. Well, two more things I want to talk about. One, I just want to mention quickly. In addition to the binomial theorem, we talked about the multinomial coefficient. That was our n choose k1, k2, all the way up to kj. This was like we started class with. This is how you rearrange the letters of multinomial. This is our n factorial over k1 factorial times k2 factorial times all the way up to kj factorial. Talked about this last time. This is called the multinomial coefficient because of the multinomial theorem. Which says that the coefficient of x1 to the k1 times x2 to the k2, blah, 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 xj to the kj, in this expansion, x1 plus x2 plus all the way up to xj, all to the n power. So instead of just x plus y, I'm adding together j different things. If I want this particular power, then I want n choose k1, k2, all the way up to kj. So quick example, if I take x plus y plus z to the 6th power, I'm not going to write what that's equal to, but the coefficient of x y cubed z squared is 6 choose 1, 3, 2, or 6 factorial over 1 factorial, 3 factorial, 2 factorial, which comes out to be 60. Exactly right. In order to have a valid multinomial coefficient, we need, maybe I'll add that in red. We need n to be equal to k1 plus k2 plus blah, blah, blah plus kj. Right, there is no x times y times z term in this. Everything has degree 6, meaning that the powers of the x's plus the powers of the y's plus the powers of the z's all add up to 6 together. Okay. That's all I want to say about the multinomial theorem. The last thing I want to talk about today is to go back to set theory a little bit and ask the question, is size of A and size of B enough to determine the size of A union B? No. Right? We need to know more. If, for example, I told you that we had 35 math majors and 47 computer science majors in this course, which is not true, I just made up these numbers, or it could be true, but I didn't check it. Does that mean that we have 82 people studying math or computer science? And the answer is not necessarily, because you can have a double major. Oops. Just try that whole word again. What about double majors? So if I look at my Venn diagram, if I know that there are 35 people in the left side, and there are 47 people in the right side, that does not mean I have 35 plus 47 people, because the people in the middle got counted twice. A intercept B gets counted twice. So what we have instead is that the size of A union B is equal to the size of A plus the size of B. Count everything in green, count everything in blue, but I've counted the stuff in the middle twice, so I subtract off once the stuff in the middle. And now the stuff in the middle is only counted once. A quick example of how to use this result. Suppose a full Winnipeg to Minneapolis flight has 87 seats. There are 53 Canadian citizens and 41 American citizens. How many passengers have dual citizenship? Chat has the right idea, but has ended up with a negative number, which is bad. We don't want to owe anyone dual citizens. So let's make our set A our Canadian citizens and B our US citizens. Then A union B is the people on the flight. And A intersection B, that's our dual citizens. So our formula says A union B is equal to size of A plus size of B minus size of A intersection B. So how many people are on the flight? We got 87. We've got 53 Canadians. And we've got 41 Americans. And then minus, this is our dual citizens, D. And so if we solve for D, we want D is 53. It's not even. Letters, numbers, plus 41 minus 87. So close, but that would have given us a negative number of dual citizens. So good. This gives us 94 minus 87 is 7 dual citizens. Just an example of how we can use this result. Speaking of flights from Minneapolis to Winnipeg, I guess I won't quite be on one of those yet on Tuesday, but next Tuesday I'm traveling. I'm traveling back to Winnipeg. I have a thing on the weekend and on Monday, and I'm returning on Tuesday, so I cannot do a live lecture on Tuesday, for which I apologize. I will pre-record a lecture. I will make it available probably sometime over the weekend, but I encourage you to spend class time watching it. If you really like the live lectures and you're free right after this, Dr. Gunderson has a lecture from 10 to 11:45, 10 to 11:15 rather. And I've spoken with her. She says you're welcome to sit in on that lecture if you want. I think they are a little bit ahead of us, so you might be slightly confused, but you're welcome to sit in on that lecture. Of course, I will also post the lecture way ahead of time so you can watch it during this normal session, and then I will be back as long as flights and everything go okay, which I believe it should be. I'll be back to live lectures Thursday morning. So if you're currently watching this for the first time on YouTube, nothing will change. But if you are here for the live lectures, I do apologize for that. I do like doing the live lectures, but same sort of thing, maybe fewer jokes. On Tuesday, you'll be able to watch it. If you want to watch it a little early, it'll be up a little early. But anyway, that's all I have for you today. I will be around for office hours as normal and stop the recording here by YouTube.